Welcome to the law of cosines. So now we have triangles that cannot be solved with the law of sines. They're just impossible to solve because you have no matching pair, right? If you try to find the matching pair of A's, it doesn't exist. Likewise for the C's and the B's. So we need a new law of trigonometry which covers non-right triangles when you don't have a matching pair for the law of sines. And you see there's really just two cases. You're only ever going to have two types of law of cosines problems. You're going to have this scenario where the angle is between those two sides, it's in between, or you're going to have this scenario on the right where you only have three sides. And of course, you can't possibly have a matching pair there since there's no angle given. So those are your two types of triangles that we're going to be solving. And therefore, it shouldn't be too surprising when you see two different variations of the law of cosines. I have one variation right here where I'm trying to solve for a side, in this case, little a. And I have another variation down here where I'm trying to solve for an angle, the angle big A. Okay. Now, you'll notice if you want to solve for an angle, okay, this one down here, if you're trying to solve for an angle using law of cosines, you need all the other sides, all of them. So that points to a strategy. The first thing you should try in law of cosines is finding all the sides. So if you have a scenario like this one, my first job is to figure out what little a is. And then using little a, like say I figure that out, I have now all three sides. I can go find another angle. But if I'm starting with this triangle on the left, I can't get anywhere until I find little a. I need three sides. That's the most important thing for law of cosines. Now, I'm not going to go into a specific example here, but I want to show you several other forms of these equations. And I hope you'll notice some symmetries about them, some similarities between them. A squared plus b squared, a squared equals b squared plus c squared. Does that seem familiar? This is basically the Pythagorean theorem with a modification. Okay, and that modification is there because we don't have a right angle. Okay, the derivation of these things is actually quite nice, but we're not going to go into that here. But there are other patterns. Let's say we wanted a side b. Okay, I don't know what b is, but I want that. Well, watch what happens here. It's the two sides. Hold on. If I want b squared, it's going to be a squared plus c squared minus, and again, minus 2ac cosine b. Okay, do you see how there's a pattern that I'm following here? The side on the left is not going to be anywhere on the right, but the angle matching the side on the left is. And likewise, if I wanted to do c squared, it would be a squared plus b squared minus 2ab cosine of the angle c. All right? So I think these are worth memorizing. You'll get to use them quite a bit in this chapter. And now I want to talk about the angle derivation. So you have here cosine a, and you'll see that that's just a rearrangement of this first one. All I did was I rearranged that first one to get cosine by itself right there. So you get cosine by itself, and then your next step is do the inverse cosine, and you're done. Okay, right? Here's what I'm talking about. We find cosine of A, and then I say, oh, wait a minute. Well, that just means the angle A is the inverse cosine of this whole thing. Okay, so you calculate that nasty fraction, take the inverse cosine of that, that's your angle A. Okay, but let's just leave it in this form because it's a little prettier to just talk about cosine A. Don't have any of those, inverse signs and brackets and all that. So likewise, I can write other forms of this where cosine B equals a squared plus c squared minus b squared, and I hope you'll see the patterns here, 2ac. And then the last one is cosine angle C equals a squared plus b squared minus side c squared and 2ab.